So regarding the last question, related to the video that I asked you to watch about the bias trick, the slide has a typo. Huh?
The first slide, right?
Yeah. What was the slide? Let me see. Yeah. Yeah, this one. So yeah, really the bias is a 1.13.2 and negative 1.2, and yeah, it's a little messy, but let's see. So this guy, yeah, this guy should be placed over here and over here, right? Okay, so that is typo. Yeah, regarding the first question of taking the quiz, the first quiz for students who took registered the class later. I will give the opportunity to take the first quiz. Today is Wednesday, so after right after our break, or in the next class, you guys will have a chance to take the quiz. Okay, and have you watched the multivariable chain rule? And did you guys understand it? Yeah. So that actually, regarding backpropagation in the neural network, that part is still not entirely clear to me. So I'm a little bit uncomfortable because I didn't fully understand that part, but at least that lecture gave some rough kind of intuition about why the multivariate chain rule should work. And let's see. See if we have a slide over here. So, or maybe let's use this. So suppose we have a single node over here that is branching out into two. Okay, and then after branching out, we don't know what kind of layers or network layout we will have after then, right? But what is always true? It is always true that our loss function is a scalar value. So loss function cannot be a vector, right? So that loss function will always arrive at the single scalar node, right? So in that case, given whatever internal node or layers we have, we can just think of this as maybe, so let's call it denoted as t, and then this one is f of t and f of maybe g of t. Okay, and then the rest of the function will be f of t and g of t will be our input to the function corresponding to this part, and that function, let's call it as an f h, and then this function will have a single scalar output, right? Okay, so now although we don't know the specific details about this part or the f, but we can think of this t is branching out into two nodes, and then after going through some function that will be merged into a single node, and thus the gradient is always generated from this particular node. So if the current output or the loss value is maybe negative log 1/4, for example, I mean in the case of softmax loss, and then we can think of their gradient, right? And then the gradient will be generated, and then this gradient will be backpropagated, and then the gradient will arrive at this node, and then this forward propagation value of this FG and FT and G of T, and then their corresponding. Okay, so it's our H, and so we want to obtain D of T and D of an H, right? So this is our the biggest loss function that will produce the final output, right? So in this case, it is represented in this form, right? So what is this guy? This guy is okay, so more exactly, so this is the node, and then even though it can branch out, but the branching is done inside of it, and then we can think of it as this guy, right? So the forward propagation will be placed over here, and then backward propagation corresponding to this node will be placed over here, and that value is, so this is our node X and Y, and so the back propagation value corresponding to this part will be this guy, and also forward, and the back propagation value, and this value will be corresponding to this value, right? And then here we have T, but that is just so let me just give an example. So it is multiplied with the 3 times and the T, and that way suppose our X or this node is like 3X. So in this case, this gradient will be multiplied with the 3 because of the gradient switcher, right? In the case of a multiplication gate. So it's just a specific example, but yes, this guy times 3, right, will be the gradient coming from this edge. But yes, suppose the gradient is over, it's 2 over here, and then the gradient will be 6, right? And then G of T will be, let's just make it an example, T and maybe another node, and let's just think of the multiplication gate, and then this value is maybe 4, and then the gradient is 5, and then this edge and its corresponding gradient will be 20, right? Because this value times this value will be the gradient of T coming from this edge, right? Sorry for the messy figure and the incomplete example, but I hope you get the idea, right? And then the point is, I mean, we have no problem of obtaining the gradient corresponding to this edge or this edge, right? But those two are actually, the most important part is that we have to add those two gradients when when this node were branched out, right? So that is because, I mean, so what is this value? dt of dx over dt. So that is 3, right? Because this node is just 3 times t, right? So that way, this partial derivative with respect to t is 3, and this guy is 4, right? And then, yeah, they are added together, right? And that is because, we want to move t. So current. Suppose the current t is maybe 7, and at 7, we want to move or nudge this value of t with +1 or -1 or unit length, right? And then we want to know its gradient or the changes due to this little nudge with the unit length of 1 in the difference of t, okay? But that difference, resulting difference, it should be counted in the final function h, right? Because that final function h is our entire, can be viewed as an entire function after taking those two as an input. Okay, so this is the final function that will produce this loss function, and then we want to know the difference or the changes due to due to the unit length change of t, right? But if t is changed by 1, and then that will incur or occur the changes in terms of x and y, which is f of t and g of t, which is corresponding to this and this node, right? And so this guy is so it will also have the forward propagation value or the current point. And then if t was changed, so what is the current value here? What is the f of t? So f of t was defined as 3t, 3 times t, and so the current position will be 21, and in this case it's 4 times t, right? And if t was 7, and then it is 28. So this is the current point. And then now after changing t by the unit length, and then it will, it is changing 3 with the amount of 3 and amount of 4 for f of t and g of t respectively, right? And then altogether this vector, right? So what is the length of this vector? So it is like 5, for example, right? So in this case, so this guy is occurring the changes in terms of this vector, which can be decomposed, or this is a d of, so this vector is d of f plus d of g, because this can be viewed as d of f, so this is d of g, right? And then overall, this kind of changes will actually cause some amount of changes in h, because this f and g will be used as an input to h, right? So d of t, or this increment of 1 in t, will cause the changes in both of f and g, and those changes will also be reflected into this function h. And so so that way those two changes should be added together, because this guy, this changes is not only making the changes in f, but also changes in g. So I just reviewed what we studied in the YouTube video in the Khan Academy, but I'm not sure if it helps you understand better about the class, the lecture videos. But anyways, once we understand this, and then it has, it is used quite often in many of different, a little bit more complex or complicated neural net scenarios. Okay, and then let's see. And I believe you understood the backpropagation of this. So what is this called? What is this layer? it is called sigmoid, right? Or yeah, more exactly, it's a logistic regression because we are taking the input of x1 and x2. Yeah, and then they are linearly combined. No, x0 and 1 will be our two input values that are linearly combined with some parameters and then added together. And then this guy is our bias, right? And then the remaining sequence is taking this value and computes the function output of the sigmoid, right? So this part is just the sigmoid function, right? Which is this guy, right? Okay, so this logistic regression can be represented as a computational graph in this form. But once again, let me just emphasize that. Where is the very first gradient initialized? Okay, where is that the very first source of the gradient? That source is our loss function, right? So we have to plug in our training data, like when x1, x0 and 1 was 1 and 2, for example. And then in this case, suppose our target variable was maybe 5, okay? And then this guy, we have to compute the binary cross entropy loss over here. And then from that single output node, which represents our loss function, okay? That loss function will be the very first source of our gradient, right? And then the gradient will be backpropagated, one by one, in the backward order. And then it will reach, the gradient will reach at this point, right? But here the gradient is just set as 1, right? So this is not the actual gradient from our loss function and from our current parameter and the data, right? But we can just safely set this gradient at this whole unit, the gradient at the final node within this sigmoid output as just 1. It is just okay to set it as 1 because the important part is actually the ratio. When setting it as 1 and then the gradient gradient with respect to W0 will be what in this case? So the gradient at this point is 0.2, right? And then what is the gradient corresponding to W0? So again, we have to use a gradient switcher. So this guy times this will produce the gradient. So negative 0.2 will be our gradient, which corresponding to W0, right? So are you guys following this? Okay, so this gradient was obtained by just setting this gradient as 1, but the actual gradient when just doing the backpropagation all the way from the final loss node, okay, and then this corresponding gradient will not be 1, and so suppose that loss was that gradient was 3, right? So in this case, through our chain rule, what will be the corresponding gradient corresponding to this node? It is just simply multiplying it with 3, right? So does it make sense? 이해가요? 네. Okay, so that's why we can modularize or we can implement this forward and the backpropagation separately for each of the node or each layer. Okay, so in each layer, suppose we use maybe linear, fully connected layer, and then maybe softmax layer and so on. And then this linear layer, we can just implement or define the forward propagation only for this module, and also we can implement the back propagation module only for this layer. Okay, and then the corresponding gradient can be just assumed as 1 and 1, for example, and then assuming it, and then we can obtain the gradient corresponding to those input nodes and also the involved parameters. Okay, and then that kind of back propagation is later multiplied with the actual gradient that is that arrives at this particular node. Okay, so if that particular gradient value was 3 and 2, and then we can just simply use this 3 and 2, and then how we multiply, and then just simply multiply the gradient that we obtained in this layer or back propagation in this layer when setting it as 1. Okay, and then we can just simply multiply this gradient. Okay, I mean, I'm not sure if I understood it. I mean, I explained it properly, but you will have more, clearer idea about what this is by handling a few more examples. 요거요? 네. 요 3이요? 요 3이요? 그러니까 이게 원래는 이제 리니어 리그레션을 만약에 한다면 이건 로지스틱 리그레션이라 이제 L2 로스를 쓰는 게 좀 말이 안 되긴 하지만, 이제 실제 파이널, 그러니까 컴플리트 컴퓨테이셔널 그래프, 완전한 컴퓨테이셔널 그래프는 여기서 끝나는 게 아니에요, 사실. 어디서 끝나냐? 이게 O가 이제 타겟 베리어블 Y로 있고, 그래서 여기서 나온 거가 여기서 나온 거 이렇게 빼줘갖고 또 이게 공간 좀 여기가 또 제곱이 되고, 그게 우리의 로스 펑션이고 얘가 미니마이즈 되도록, 그래서 여기서부터 그레이디언트가 1이 만들어져서 백 프로퍼게이트가 돼갖고 여기에 도착을 하는 거거든요. 그레이디언트 값이, 혹은 여기에 도착을 하는 거여서 저 값이 실제로는 이제 1은 아니고 뭔가 이제 뒤에 더 있다는 거죠, 컴퓨테이션 그래프. Okay, so again, the reason why we can have a different values of the gradient corresponding to this position is because, up to this point, it is not a complete computational graph that we have that fully represents our loss function. Our loss function, we'll need more, more layers or more steps in our entire or complete computational graph, right? So in the case of an L2 loss, so this is the target value, and then we take the difference and then take the square of it, and that will be the final output or final function value that we want to minimize. So the very first source of the gradient is that node, right? Any other questions? Okay, and then 이건 누가 질문한 거예요? 용수? 성이 뭐예요? 장용수? 네. 내가 되게 군대 때 만난 친구를 애타게 찾고 있는데 그 이름이 장용수. 나는 참고로 군대를 직접 갔다 온 건 아니고 병특하고 4주 훈련을 받았는데. Okay, so in the case of logistic regression, suppose we obtained through this logistic regression, suppose we obtained the output as 0.7. So this value is the output of the sigmoid function. The range of this output should be always between 0 and 1, right? And then suppose we currently obtained the output as 0.7, right? And then suppose the label of this corresponding data was 1. And then what will be the loss function in this case? You guys know the loss function is defined as this, right? And then we only use this part because our, so this guy, our final prediction value. Yeah, so let's call it as y, and so this is y, and this is a loss with respect to I, right? So in case the label is 1, and then if this value was 1, and then loss will be exactly 0, but if it is smaller and smaller and getting closer to 0, and then loss will be infinity, right? And then the question is, what if we use just the squared loss? So in this particular case, this is the current prediction value, and this is the target value. And then what will be the corresponding loss graph? The loss graph will be simply y minus 1 and squared, right? And then what will be that graph? It's like this, right? So, yeah, given this function that is defined, defined in the entire region of y, the possible y values will only existing in between 0 and 1, right? So this part will only matter, right? So in this case, let's just compare between these two loss functions. So one kind of important difference is that as the prediction values getting closer to 0, and then in the case of this binary cross entropy loss, the loss will become infinity, right? But in the case of squared loss, still the loss will be just a finite number, which is only just 1, okay? As small as just 1, right? So in this case, like, even if a patient came, and then even if he really has a maybe lung cancer, but our model is saying that, okay, this guy has no cancer at all with 100%, which corresponds to like 0 probability of having a cancer. So suppose that is our prediction output. And then in that case, the loss will be, we just assign the loss in that case as only a finite value of 1, okay? But in that case, it is actually, in practice, it is really serious situation, because our classifier did a misclassification with the entirely wrong manner, right? So we have to take it seriously, and so it's more reasonable to give a much higher loss value. But even if you use just the squared loss, your model will probably work, okay? But theoretically or in principle, the typical way or standard loss function in the case of classification problem, we have to use a cross entropy loss or softmax loss. Any other questions about it? Okay. Okay, so back to this sigmoid example. So once you follow this derivation, okay, so here, one interesting aspect is that our gradient is represented in terms of our output, not in terms of an input, right? So what does it mean by, if y is equal to x squared, and then suppose we want to obtain the gradient with respect to x, and then we know it is 2x, and it is basically a function of an x, right? But can we represent this gradient function in terms of y? So we can of course represent it 2 times square root of y if x is larger than or greater larger than or equal to 0, or if it is a negative value, then this guy, right? So in principle, representing our gradient function with respect to x or with respect to y, so they are equivalent. So you can freely choose, you can freely use either of them, right? So let's imagine the forward path. So x was 2, and then the forward path will give you the 4 as an output corresponding to the node of y. So in this case, suppose the backpropagation came from here and set it as 1. Okay, let's just set it as 1, and then what is the corresponding gradient? And then it will be just 4 because of this. So in this case, we plug this guy, right? But we can just obtain this value by using this representation, although it's a little messier than this form. So in this case, which value should we plug in to this function? Of course, we should plug the y value into this representation. So we have to bring this guy, right? So yeah, so its x value is positive 1, and so we have to follow, or we have to take this function representation. And so if 4 is plugged in, and then it is still giving the 4 as our backpropagation value, or this gradient with respect to x, right? Okay, so once we obtain this gradient of sigmoid layer. So yeah, this is the sigmoid layer. So here, this x is which node? Which node does this x correspond to? Is it these x's or somewhere else? So this subpart is our sigmoid function, right? And then the sigmoid function will take the scalar input and produce a scalar output. And yeah, so here we just consider this position as x, right? And then this whole part will be our function f, or our sigmoid function. Yeah, this is sigma of an x, right? And then when x is 1, and then this function value will be 0.73, and then if the gradient at this point was 1, and then how can we compute the gradient corresponding to x, or more exactly d of an x, d of f of an x, or yeah, this guy is a sigmoid function, right? And so we want to obtain the gradient value corresponding to this, but we can represent our gradient function with respect to this input value x, but also we have a freedom, or we have another choice of representing the gradient function with respect to function output y. Okay, and so these two are equivalent form. That's just a different in terms of using the variable to obtain the gradient. Okay, just like this case. So this is the same gradient function, but with respect to, or when using the input variable x, but here the input variable to this gradient function will be our y value, right? Okay, so again, we can freely choose either of them because they will produce the same value. Okay. So in this particular sigmoid function, between this representation and this representation, which one is simpler? This is simpler, okay? So we typically use this representation in order to compute our gradient for the sigmoid function, okay? Okay, then let's just also think of this function in more detail. So sigmoid function, has this shape, right? So it has 1 as an upper bound and 0 as a lower bound. And at 0, what is the function value? It's 0.5, right? So in this particular case, what is the forward propagation value? So x was set as 1, right? I mean, this value is not arbitrarily set, right? Because that is the output from the lower layers, right? So from the layers on the left, yeah, we forward propagated, and that way we obtained this forward propagation value at that moment, at that point as 1. Okay, so that. Okay, and then it will be somewhere around here. And then what is the function output or y value? It is this guy, 0.73. 0.73. Okay, and then again, this guy or this guy is the same gradient function, which is this d, yeah, this guy over dx, right? Okay, and then let's use this function to obtain the gradient. So that gradient is computed as follows. So the function output of the sigmoid will be always between 0 and 1, right? And then the first one is 1 minus sigmoid output, which is 73. And here again we are using y value instead of an x value in order to obtain or compute the same gradient. So this value is 0.27 and this value is 0.73, right? So we are just multiplying these two, and then this value will give you the gradient, right? Okay, and then what's the meaning of the gradient? I mean, when given x and y in this form, and then at x being 1, what is the meaning or physical meaning of the gradient? So that is the slope at this moment, right? This guy, right? So this slope is represented as this representation, right? Okay, and then in this graph, just looking at this graph only, and where is the steepest gradient position? I mean, where is the x position that has the largest gradient value or slope? That will be at 0, right? And 0, the gradient will be this, right? And what will be the slope of it? Slope is also defined as this gradient function, right? So yeah, we need a function output because this guy will use the y value in order to obtain the gradient. So x is 0 during the forward propagation, and then y is what? Y is 0.5, right? And so we have to plug this 0.5, which is our y value, in this formula. And so it is 1 minus 0.5 squared times 0.5, which is 0.25, right? And so what is the slope of this steepest gradient part? So that is only 1 over 4, right? 1 over 4. Okay, and that can also be understood by looking at this function only. Okay, so let's just forget about the original function shape, but let's just look at this gradient function. Okay, and this gradient function will take the input as y value or sigma over x, right? And that value is between 0 and 1. And then what is the possible outputs of this function? So it's 1 over sigma x, 1 minus sigma x, and this guy, right? Where this guy is 0 and 1, right? And then, yeah, let's just try to, represent it as this function, and then x minus x squared, right? And then let's just rewrite it into this form, x minus 1 over 2 squared, and then plus 1 over 4, right? And so it has the graph of 1 over 2 and 1 over 4, and then like this, right? Okay, and then what is the possible range of this input value? I mean the sigma upon x. That is only this part, right? So the possible input value will have only this range, right? Okay, so what's the meaning of this function again? So this is representing the gradient value. Okay, so when the function, when this sigma upon x was close to 0, or just to say, let's say just it's such 0, and then what is the gradient value? It will be 0, right? And let's just redraw this sigmoid function over here, and then when is the function output being 0? It's around here, right? Because in that part, I mean, it's not becoming exactly 0, but it's close to 0, and that's corresponding to negative infinity for x value, right? So in the forward pass, and then the forward pass will have this negative infinity, and then will be mapped into 0, and then what is the gradient? I mean, like this node, and then this is the forward propagation values, and then the backward propagation values will be 1 times the gradient at this point. I mean, this is giving the gradient, right? And then it is giving 0, right? And so the gradient corresponding to this node is what? 1 times 0, because we give a 0 gradient value, right? And again, what is the slope at this point? The slope is just close to 0, right? Okay, so let's just move gradually our y value from 0 to 1, and that is corresponding to moving y value from 0 to 1, and then let's just think of the slope. Slope is almost 0, and then it is gradually increasing, right? That increase is represented as this part, right? And then at this point, the gradient is the maximum, right? And that value is what? 1/4, and then gradient is now start to decrease, right? Like this. So it gets decreased as the sigmoid function output gets close to 1, right? Okay. And any questions so far? So it's a little
영화 보일 때 학습이 잘 안 된다.
네? 네, 맞아요. 그래서 이게 이제 그레디언트 베니싱이라고 하는 이제 뉴럴넷이 몇십 년 동안 이제 발전을 못하게 된 어떤 가장 큰 원인인 셈인데, 그걸 좀 설명을 또 해줄게요. Any other questions? Okay, so this kind of thing is related to the gradient vanishing problem, which is quite notorious. That prevented the neural net's development or advancements for the last few decades. Okay, so neural net was invented maybe 1970 or 80. I'm not sure, but for almost 20 or 30 years, it was just abandoned. Okay, so when I when I took the machine learning class, when I did my PhD, and the teacher or the professor didn't teach the neural net at all, right? Because about maybe 10 years ago, it was considered as kind of useless, because even though the model is quite fancy, but it was in practice it was not trained properly, and the main reason for not being able to be trained was because of this simple fact of having this sigmoid, and then once we pass our sigmoid layer, so this is the sigmoid, right? So given the sigmoid input and output, suppose we have some gradient over here, and then this gradient will be multiplied. So if it was 1 and then 0.73, and then the gradient will be around 0.2 and point, yeah, 0.3 and 0.7, and so it's like 0.21. So that is the rough output of this guy, right? When the function output was 0.73, right? So that means the corresponding slope is only 0.21, right? And that gradient value is multiplied with the gradient at this point, right? So if it was 1, and then this guy is scaled down by the factor of 0.21, right? And so gradient, I mean the magnitude or the absolute value of the gradient has been decreased, right? And then suppose our parameter, I mean, where is our parameter to update through the gradient descent? The parameter are over here, W012, right? And then suppose we have the gradient over here, and then in this case, the gradient has already reduced or decreased into some smaller value, right? And then this smaller value, I mean, yeah, it's an add gate, and then it's a duplicated, right? And then this gradient has not been reduced or decreased at this point. Yeah, but it's already quite small value, and then yeah, even though through this gradient, like duplication, and then in this case the input value was only -1, and thus the final gradient that arrived at this parameter for our gradient descent update. Okay, so this gradient will be already become small because of this sigmoid function and the backpropagation step that passing back through this sigmoid gate. So that is called the gradient vanishing problem. I mean, this kind of effect or this phenomena gets even worse and worse when stacking our neuron net or this kind of layers more and more. So for example, if we have 3 nodes, and then suppose we have 2 nodes, and this so far this is linear layers, and then we apply the sigmoid, right? And then obtain the output over here, and then this value will be also going through the another linear layer or fully connected layer, and then we also apply the sigmoid as well. Okay, so suppose we have some gradient value starting from, gradient always starts very first from the loss node, and then suppose our gradient value was maybe 1 and 1, and then passing back through this sigmoid through backpropagation, gradient is scaled down. Okay, and then some parameters that is involved in this layer will be updated using this already small gradients. But also, what about this part? So it's like x1, x and w and b. So suppose this guy is wx plus b. Okay, and then let's just reach out to this node, and then it has to be scaled down first, and then also through some gradient, and then it also scaled down even further through the second gradient, right? And thus those small values that has at most the maximum value of 1/4 or 1/4, right? So that is the maximum possible value of the gradient from the sigmoid, right? So at each layer, the gradient will be like scaled down at least 1/4, right? So gradient becomes smaller and smaller, and so the gradient arriving at this parameter node that is in the lower layer, the gradient will be almost 0, right? So if we stack the 3 layers, and then it has to go through 3 sigmoid, and so it's like 1/4 to the power of 3. So that is the scale down factor. So that way the gradient value keeps small and small, and thus the gradient will be almost 0 when arriving at the parameters in the lower layers. And so there is no way to update these parameters in the lower layers. Okay, so that is the notorious gradient vanishing problem.
Is there any techniques that we can maybe identify the gradient vanishing problem?
What's that?
Is there any techniques that we can use to identify that the gradient is actually vanishing?
Yeah. So yeah, one aspect that we can think of about when the gradient vanishing becomes a severe problem. Okay, so that is related to our forward pass as well. So suppose our forward pass, during our forward pass, suppose our input value to the sigmoid function was really far from 0, right? So some value like 100 or negative 100 or negative 1000 or something like that. So in this particular, those large values, and then what is the gradient corresponding to that point? It is close to 0, right? So 1/4 is a maximum value, and as it gets farther and farther from the origin, the gradient gets smaller and smaller, getting close to 0. And thus, in that case, gradient will be almost killed when backpropagating through this this sigmoid node. So when doing the forward propagation, we can already kind of identify, okay, the gradient vanishing will occur. When those input value to the sigmoid, if that value has a large absolute values, and then gradient vanishing will occur. So there is a remedy or some additional techniques that can compensate this kind of problem, and that kind of technique is called what? Have you heard about this batch normalization? So you will study this batch normalization in few weeks, but this is basically additional layer that we stack in our neural nets. And this batch normalization layer is usually put in the middle or between the linear combination output and also the sigmoid. So, so what is this input value of our sigmoid layer? So that is typically made through this linear combination, right? So some linear combination or fully connected layer, and then go through nonlinear layer of sigmoid, right? So this value can sometimes have a really large absolute values that will kill the gradient, right? And so we typically add special type of layer called batch normalization in between those two, right? So we typically add another layer over here, which is called the batch normalization. And that batch normalization, the effect of this batch normalization is that given whatever input ranges of this value, okay, this value, suppose typical output of this value was somewhere around here, okay, so it's usually between 100 or maybe 200. So those are the current forward propagation value corresponding to this node for whatever data that we have in our training data. Okay, in that case, for our training data, the gradient will always be killed because those gradient values will become 0, right? So this kind of batch normalization is just collecting all the forward propagation value corresponding to this node when using each of our training data. Okay, so suppose we have 10 different training examples, and then we would do the 10 different forward propagation, and then we will collect, we can collect 10 different values corresponding to this node, right? So we have 10 numbers and look at their distribution, and if those 10 different values are mainly lying in this region, which is really far from 0, and then that means the gradient are killed, and thus all the parameters behind this layer will have no way to get updated because the gradient will be already killed or become 0. And so once we identify the range of this node, which will be given as an input to the sigmoid, and then we just additionally adjust their ranges so that the ranges becomes close to 0, right? So this range becomes around 0, right? So this is this batch normalization. And how do we do that? How do we do that? How do we do this batch normalization? We just compute the mean and for example, variance as well by using the 10 different numbers, and then we subtract the mean and then the scale down with respect to this standard deviation, which is the square root of a variance, and then that way we can just we can always guarantee that the input value and their typical range to this sigmoid function is always near the center or the 0, so that they at least give some non-zero gradient values, okay, to avoid the gradient vanishing or gradient, gradient being killed. Yeah, we all want to avoid that. Any other questions? 네.
아까 그레이디언트 베니스 설명하실 때그 시그모이드를 쓰는 레이어가 이제 멀티레이어의 중간에도 쓰는 거랑 있었는데 시그모이드 레이어의 중간에 써야 하는 경우가 어떤 경우가?
중간에 써야 하는 경우요. 그러니까 여기 이제 리니어 레이어 뭐 이걸 FC라고 하고, 그 다음엔 뭔가 이제 인터미디어트 노드를 만들어서 첫 번째 히든 레이어에서, 그래서 이거를 시그모이드 안 통과하고 그냥 또 리니어 레이어를 또 쓰면, 이게 지난 시간에 얘기했던 이제 리니어 레이어를 두 개를 겹치면 이제 하나의 리니어 레이어를 쓴 것과 뭐 대동소이하다. 그래서 이제 난리니어 이펙트를 좀 만들어주기 위해서 이런 난리니어 액티베이션 펑션 or 난리니어 유닛을 항상 우리가 넣게 돼요. 다만 이제 저거를 이제 시그모이드로 넣느냐, 아니면 렐루로 넣느냐, 10H로 넣느냐, 아니면 기타 뭐 다른 좀 더 이상한 펑션들을 넣느냐는 우리의 초이스긴 하지만, 일단은 뭐 시그모이드 그리고 10H도 마찬가지로 저런 비슷한 이제 한계점들을 가지고 있는데, 어쨌건 저걸 넣는 거는 일단은 넣어야 되기는 해요. Okay, yeah. So yes, so using the nonlinear layers is inevitable because if we stack just the linear layers and then as we saw in the previous class, it will be represented as just a single linear layers, right? So stacking the two linear layers without with no nonlinear layers, that can be always represented as one single layers, right? So in that case, we don't have a rich like representation capability of our model.
그러니까 배치를 쓰는 이유가 그 퍼포먼스의 스테빌리티를 안정성을 추구하고자 쓰는 거잖아요. 그래가지고 인풋을 지금 지로민으로 쓰는 건데, 그러면 그 인풋 지로민을 저희가 계산을 해서
네. 그러니까 이제 뭐 저거를 통해서 성능이 좋아질지 나빠질지 잘 모르는 거고, 그러니까 엄밀하게 말하면 저 노멀라이제이션을 해서 뭔가 이 레인지를 항상 0으로 맞춰주자, 그게 사실 성능을 더 좋게 만드느냐, 일단 그건 잘 모르겠고, 그건 그렇죠. 안정성. 그리고 그 안정성이라는 게 정확하게 뭐냐, 바로 이 뒤쪽, 그러니까 쌓아도 이제 이 뒤쪽에 있는 그러니까 좀 처음 단에 있었던 그걸 이제 로어 레이어라고 표현을 하는데, 이게 로어 레이어에서의 파라미터들 한테도 그레디언트가 이제 난제로 값으로 도착하기를 우리가 바라는 거예요. 네. 그렇게 해야 최소한 이게 전체적으로 학습은 되니까, 얘네들이 꿈틀꿈틀 그레디언트 디센트에서 업데이트가 되니까. 네.
배치 노멀라이제이션이 각 노드마다 적용되는 건가요?
네.
그럼 너무 비용이 비싸지지 않나요?
비용이요? 어쨌건 이제 평균 빼고 분산 혹은 스탠다드 디비에이션을 나누고 하는 거니까, 계산상에 뭐 추가되는 계산이 당연히 이제 들어가긴 하지만 뭐 계산이 그렇게까지 많아지지 않아요.
그럼 그 배치 노멀라이제이션 쓰는 이유가 엑셀 값이 너무 커지면은 그레디언이
베니싱, 네네.
베니싱해서 그런 건데, 그러면 만약에 렐루 같은 경우는 커지면 그 그레디언이 더 이게 하는데